Hello, everybody, and welcome to our webinar on vibration control for original equipment manufacturers of industrial equipment and scientific instruments. My name's John Morgan. I am the marketing manager here at TMC. Mike Georgalis will be our presenter for the day. I just wanted to do a little housekeeping. We are recording the webinar, so we will send a link to the recorded webinar for you to review or share with your colleagues. We are also leaving time at the end. So on the right, you can see a section where you can ask questions. So, please ask us any questions you have, and we'll leave, 15 minutes at the end to address those questions. So with that, I will turn it over to Mike Georgalis. Mike.
Thanks, John. Good morning, good afternoon, good evening, everybody. Thank you all for signing up for our next webinar. This one we're focusing on vibration control for OEMs of industrial equipment and scientific instruments. My name is Mike Georgalis. I'm the North American Sales Manager for TMC. I've been with the company now for going on 9 years. I've got a background in physics. I've worked with vibration control while here at TMC for a lot of different applications, from photonics to semiconductors to life sciences. Sometimes we're installing platforms and doing floor vibration control at the end user site. A lot of times we're working with OEMs to build vibration control into their instruments, and that's what we're going to be talking about in today's presentation. We're going to start off from the top down. We'll do an introduction to TMC, who we are, what we do, and we're going to talk a little bit about the types of applications we serve and what is ultra precision. That's the kind of field that's got a lot of interest in it nowadays and for a long time. So we're going to talk a little bit about what drives the ultra precision applications, and then vibration 101, what causes payload vibration, and then we're going to go into isolators and the types of systems that are going to be going into some kind of tool or instrument that might be used in an ultra precision application. We'll talk about combining isolation systems, because you guys have probably dealt with very complex isolation systems and putting systems on top of another, and then how do they interact with one another, and all these kind of things. And then we're going to jump into a couple examples of how sensitive instruments are affected by vibration. So we'll look into a little bit about the mechanics from a pretty qualitative standpoint for like a scanning electron microscope, and for example, some sort of wafer inspection tool. I'm using wafer inspection in the semiconductor sense in a very, very general sense. We're talking about, they could be defect analysis or, surface metrology or that kind of thing. It could be SEMs, it could be interferometers, those types of tools. But, wafer inspection, what we're really going to be focusing on is the moving stages inside wafer inspection tools and the vibration that's generated by those. We're going to talk about vibration mitigation in instrument design. So how does it actually get built into the instruments in different ways? And from that, we're going to jump into examples of 5 different types of ways we've integrated vibration control into different instruments. Then we're going to wrap it up with stacked systems versus integrated systems, because that kind of ties back to combining isolation systems. So we'll talk a little bit about the merits of stacking versus integrating a system. And by stacking, I mean putting an entire tool on a platform versus building that platform or building that vibration control inside the system. And then we'll wrap up with a brief conclusion and take questions. So this is TMC. We're the world leader in understanding environmental effects on ultra-precision instruments, experiments, and nano-manufacturing processes. And we've always viewed ourselves as sort of a consultant to OEMs and really to anyone who's looking to solve a complex vibration control system. What makes us unique is that we're a company of engineers. We've got all of our manufacturing, engineering, sales, and marketing. Everything is under one roof here at our Peabody, Massachusetts, just north of Boston headquarters. And we spend literally all day thinking about vibration. So when people come to us, they come to a company that really, really wants to build a custom or configured or complex or very simple solution. But we're really going to try to get into what you're working on. So you're always going to be talking with engineers. You're always going to be talking with people that really have had a lot of experience in this industry. We were started in 1969 and as Backer Lowering Corporation. And in 1979, Two alumni from MIT split off and became TMC. We've been bought by Amatec. You guys may have heard of Amatec. They're a S&P 500 company. They buy small companies like TMC, and they're pretty hands-off. We're still TMC, but we do get some support from Amatec, especially for international support, where we've got now offices all over the world, thanks to Amatec, and service teams as well. The number of employees at TMC, it's probably a little higher than 85 now. It's a little outdated. We're closer to 120. You guys, if anybody here is in the semiconductor industry, you're probably aware of how much ramping has been going on. We've been supporting semiconductor for a long time. That's led to a major ramp here at TMC. We're probably closer to 120 employees here. Most of that ramp is direct labor out of the factory. We serve electron microscopy markets, semiconductor markets, photonics, metrology, and life sciences. So what is ultra precision? And ultra precision is a general term, and it was coined by a study done by Dennis Swit at NIST. And the general feeling, the general idea is that over time, tolerances get tighter and tighter. And as things get more, tolerances get tighter and tighter, and you're trying to image and perform operations at smaller and smaller scales, you start to get vibration becoming more and more of a problem. So in the vibration world, as technology marches on, the need for vibration marches on even more. And it's obvious that that technology marches on, and NIST kind of coined these three phases. They've coined normal precision, precision, and ultra precision. And there's three different types of, general scales that those types of applications would be involved in. So a normal precision would be an automobile component. In normal precision, that's kind of a reason why a car built in the 1970s required a lot more maintenance, didn't last as long, and probably had a lot more problems than a car built nowadays. And the reason is the tolerances in the engine and in the car have gotten tighter and tighter over time. Pistons fit more easily, more tightly, and run more smoothly inside their cylinders. And crankshafts have less friction and less space and less rattling. So everything's kind of more tightly put together and more smoothly running. And that's due to tolerances getting tighter and tighter and tighter, being more and more precise. At the precision level, integrated circuits, ICs, are a really good example. And that's being driven by Moore's law. And anybody that's had any experience with semiconductor knows about Gordon Moore. He coined this theory, this drive in the semiconductor industry that the number of transistors per unit area is going to roughly double every 2 to 3 years. And so we've got this sort of linear expansion, or more or less exponential expansion of how many transistors can be fit on a unit surface area on a silicon chip. And back in the 2000s, we were talking about the node size being like 45 nanometers, but now we're looking at 5 and 3 nanometer nodes. And that's the reason that drives technology such as our consumer electronics. That's why in the 90s, you had a cell phone the size of a brick and a CD player and your own personal planner and a beeper and all these other items. But now all that processing power fits, and more, and a PC, all that processing power fits now into your cell phone. And that's all due to Moore's law, more transistors per unit area on microchips. And then you've got ultra precision technology, and we're seeing applications like cryo-electron microscopy and various transmission electron microscopy and other single molecule biophysics and other applications where you're looking down to the atomic and even angstrom scale in biological molecules to be able to view features. And this is interesting in life science because this is how, in the ultra precision world, this is how we were able to so quickly image, for example, the COVID molecule, the COVID virus. And we were able to look at those points on the viruses where the barbs stick into cells and inject into RNA. And these are tiny, tiny features on the angstrom and nano scale that really can only be, we were only had the technology to view these within the past couple of years. And the type of instruments that do these operations are a wide range of instruments. And there's, as you guys know, there's a lot of companies that do these types, that build these types of instruments. We've got nanotech and nanofab with SEMS and TEMS and FIBs, advanced like microscopy and life sciences. We've got gene sequencers and NMRs in the life science field, photonics field, not so much an OEM field, but the very large petawatt lasers and interferometry and holography and virtual reality type applications occur in photonics. And then semiconductor manufacturing is a big field for nanotech, where you're doing wafer inspection and surface metrology, failure analysis, defect review and repair, and the types of instruments for semiconductor and advanced microscopy. And all of these, some of them require their own vibration control, which is internally generated noise generated by the instrument itself. But a lot of it is also floor vibration control. And so I want to talk in the next slide a little bit about where vibration comes from and how we start thinking about canceling it. So what factors contribute to payload vibration? And when I talk about a payload in this presentation, I'll be talking about basically the instrument itself. And it's anything that might sit on top of a platform or anything that might sit on top of an isolation system. I'll call it payload. So from the ground, you've got floor vibration. It's a major contributor to payload vibration, and this is coming from the environment. Footfall, nearby rails and traffic, basically human activity, seismic activity, all these types of things that are feeding energy into the ground. We even have this geological phenomenon known as the microseismic peak, and that's the sum of all the ocean waves crashing on the shores of all the land in the world at about 0.2 hertz. And if you have a geophone that's sensitive enough and large enough, you can sense this microseismic peak basically anywhere in the world. It's all from the cumulative effect of the ocean waves crashing on the shores. So that's noise coming up from the floor. Then you've got your acoustic and barometric noise. You've got people talking, you've got other instruments and all sorts of noise and motors and things going on in a building. Then, but also pressure waves. So people opening and closing doors, or an HVAC system kicking on and off, or an elevator going up and down a shaft. These are the kind of things that introduce sound waves and pressure waves into an environment. Another contributor to payload vibration is your isolation system performance itself. So yeah, an isolation system inside a machine can help your problem and reduce some frequencies, but it can hurt your problem by amplifying some frequencies if it has resonances. So I'll talk a lot more about resonances in isolation systems on the next few slides. And then we've got noise generated from the tool itself. So you've got this external noise coming in, but a tool, these instruments themselves, they've got vacuum pumps and roughing pumps and moving stages and robotic arms and various other types of anything mechanical on there making noise and causing payload vibration, moving stages. And also the frame bending and resonances. So these instruments tend to be built on pretty robust frames, or the people that build them hope for they're robust, but a frame is always going to have resonances. So it's these steel structures that are trussed and gusseted, made from tube steel and welded together, they still have their own resonances, and you have to consider that when you're thinking about floor vibration, or when you think about vibration that's being introduced into an instrument. So the first thing that you're going to try to do if you've got vibration and you want to get rid of it is you're going to start thinking about an isolator. And these next few slides are going to focus on the types of isolators that are available in the world for vibration control. And the most simple isolator that exists is a spring. It's basically a filter. And what you get when you get with a simple passive spring is a transfer function. Really, any isolator is going to be a transfer function. A transfer function is basically a ratio of the payload motion to the floor motion. So it's what you have coming in, or coming in. It's the energy, a ratio of the energy coming from the floor or from whatever's generating that vibration to what's being produced at the top of the isolator. So you get this ratio of performance, an isolation factor, and we call that a transfer function. And the transfer function of an isolator, especially a passive isolator, starts to have different characteristics. And when you look at how a transfer function performs, a good example is this chart down on the right. And what we're looking at here is a chart with frequency on the bottom. So isolators perform proportionate. The performance of an isolation of an isolator is proportionate to the frequency to frequency of the input. And here's an idealized isolator with a resonance at about 1 hertz. And here's 1 hertz right here. And what you can see here is a very, very soft isolator actually amplifying vibration coming in from the floor. And once you get to the unity line, this is where you start to see isolation. And this is your isolation performance in isolator, these curves that are below unity. And that's where your transfer function is less than 1. And you've got and you're actually achieving isolation. So this is great, except you're amplifying at the resonance, which is just a physics fact of how isolators work. So there's one thing that you can do, unless you're looking at active systems, you start to damp the isolator. You start to add in some sort of mechanical resistance to the motion of the isolator. And damping can be done in a lot of different ways with materials, but really it's about internal friction. And as you add damping, you're effectively, as you're adding internal friction to the system, you're effectively also generating very, very weak mechanical shorting paths. So you start to transmit more vibration as you add more damping. But so the effect of adding damping, trying to damp out a resonance system is explained with these different Q factors, where Q is how much damping you're adding. And you start to add more damping, for example, at a Q factor of 10 here, you've reduced your resonance by a decade, but you've also paid the price because that extra material, that extra friction in the system is costing you high frequency performance. And so and you can see down here where the isolation line starts to come a little bit higher than the first line, you've lost a little bit of performance at 100 hertz. And so you start getting to a critically damped system, and you add more damping, you get less high frequency performance. You add even more damping, you get to critically damped, you have lost quite a bit of high frequency performance, but you've almost completely eliminated your resonant frequency. So there's the trade-off. You can get less amplification at resonance, but you are going to pay for the price at high frequencies. And that's how a passive isolator generally behaves. And most passive isolators are mass spring damper systems. And a lot of the ones that are used in the industry and are commercially available are pneumatic isolators. So they're a sealed air chamber that we put a high pressure air into. It floats a piston, and that gap in that air, that floating piston is what you place your instrument on, or your moving stage, or whatever it is. And you can benefit from the softness of that system, where you're going to experience a relatively high resonant frequency because the soft system, about 2 to 3 hertz, but you get really, really great, a really fast roll off, similar to this curve, and get a really good high frequency performance. So these are really good isolators. And for high frequencies, they do a great job of providing performance. They've got some weaknesses. They're generally soft, so they're going to shake and they're going to move easily. If you press on them, they're going to move. And if you've got low frequency vibration in your floor, for example, or in your system somewhere, these are going to amplify it because they've got that low frequency resonance. 2 hertz resonance is a pretty good, is a very, very soft spring. And a good example of a soft spring like that, if you want to think about 2 hertz, is the bumper of your car. If you go to your car and you press up and down on the bumper, you can drive your car at its resonant frequency at about 2 hertz. It's not going to bump up and down and keep going forever because it's highly damped. You got the shock in there too, which is filled with oil, and that shock provides that friction that stops that resonating, that stops that jumping down of your system. But if your shocks go, if that's ever happened to you, you'll feel it, and your car will be constantly rising up and down because you've lost that damping, and it's going to rise up and down at about 2 hertz. And that's very similar to how an air isolator is going to perform. Air isolators are also susceptible, however, because they're a sealed air chamber, so they're going to be susceptible to the ideal gas law. So if there's major pressure changes or temperature changes and expansion and contraction of the air outside of the isolator, that sealed chamber is going to want to react according to PV-nRT, and it's going to want to increase its volume to a pressure change that goes lower, and it's going to decrease its volume to a pressure change that is higher. So you've got to worry about these isolators performing in a way that could be detrimental based off of temperature and pressure in the room too. So air isolators are good. They're industry standard. They're used in a lot of places, and they're built into a lot of instruments because they provide really great high frequency isolation, but they've got weaknesses. They've got an Achilles heel. They've got susceptibility to pressure and temperature, and they've got resonance at 2 hertz, which is a very, very common resonance in large structures like buildings. And it's a common resonance that's introduced to the ground through all of the types of vibration inducing sources that I talked about in the first couple slides. So we start to think about, well, how can we get even better isolation? Well, it's active vibration isolation systems. And there's a couple different types of active vibration isolation systems that I want to talk about, and the way they are applied depends on the needs of what you are trying to cancel. The earliest active systems came in back in the 40s and 50s, where we were looking at helicopters, and helicopter pilots were having a lot of vibration in the seats. And to cancel out some of that vibration in the seats, that's when the military started thinking about these linear motor-based active cancellation systems that sensed and canceled out vibration. And when you think about an active system, what you really need are 3 components. You need a motion sensor, something that's going to sense that motion that you're trying to cancel. You're going to need a force actuator. It's going to be maybe a piezoelectric stack, or it might be a linear motor, or it could be just a pneumatic cylinder where you're varying the pressure. And you're going to need some sort of control loop. So this is software that actually controls the system. And then there's 2 types. You've got serial types and parallel types. You could take these 3 components, these key components, and arrange them in different ways. I'll talk about serial type and parallel type systems on the next couple slides. Sorry, I'm switching too fast. The parallel type system is the first one I'll talk about. This 3-die diagram on the right is a good representation of what these systems look like. Here's your isolated payload. So this could be an entire instrument sitting on a platform supported by the vibration cancellation system, or in more often cases, it's a granite mass, or the top of a table that supports a moving stage or something like that. This would be a very common type configuration for like a wafer inspection tool, which I'll talk about later. But what you've got here is you've got a sensor, which is your first component, on top of the payload. You've got your feedback control loop, so that sensor is sending a signal to your force actuator. And the system is supported by some passive spring, and your force actuator is in parallel. They're working in the same plane on the payload as the spring. So the key takeaways here are your sensor's on the payload. Your force actuator is actually not often load bearing. In this case, the majority of the load is being borne by some passive isolator. The force actuator, which may be like a linear motor, it actually isn't bearing any load of the system. So what that does is it already introduces some inherent resonances into the system. You've got the resonance of whatever this passive actuator is. If it's a passive pneumatic isolator, you've got a 2 hertz resonance already feeding into the payload. You've got payload noise and all sorts of things going on the payload feeding into the sensor, and all that information is going into the actuator, and it's trying to cancel out all of that information. Resonances coming in, payload noise coming in, actuator trying to cancel it all. So that's pretty cool, but it really limits your bandwidth. A lot of information coming into the sensor starts to limit your ability to achieve stability, where you want to cancel out noise at certain frequencies. For example, the low frequency is very, very, very difficult for a parallel type system to be able to cancel because it's got such a prominent resonance from its pneumatic support system. But what these guys really do well is cancel payload noise. So what you can do is you can take this sensor and this feedback loop and you can augment it with feed-forward technology. And if you've got known payload noise, like a stage that has a known weight and a known acceleration and a known distance that it travels, or a robotic arm that you can easily model its motion, or some motors that you know are running at some certain frequency with some certain mass, this type of information can be fed forward into your cancellation system, and it can predict that movement. And so what you can actually start to do is use a parallel type system to get very, very effective cancellation of known payload noises. And that And again, you're still using a lot of its bandwidth. They just still don't do very well at low frequencies, but you've created a system that actually controls its own vibration, its own known vibration very, very well. But it doesn't work very well for floor vibration because it's using all of its effort to cancel out its onboard vibration. The other way to arrange these systems is what we call a serial type system. And we take the same components, but we introduce a third component. And in a serial type system, you have this inner mass. And a force actuator is actually supporting the inner mass. And so what's interesting about this is that this can't be done using linear motors. It has to use some sort of stiff load-bearing actuator. And really, a piezo is the only thing, piezoelectric stack is the only thing that you could put in here to support that inner mass. And then on top of the inner mass, you have your passive isolation system. So this is usually a stiffer spring. And then this is supporting your payload. So a good example of this type of application would be an instrument sitting on top of an active vibration platform, where your instrument is this, and everything below this back line is your platform with the isolation system. You still got your three components: your sensor on the inner mass, your control loop, and your actuator. And what makes this unique is two things. One, it performs floor vibration cancellation very, very well. Because you're going to have a payload up here, and this payload is going to be a noisy payload. It's going to be moving back and forth, moving stages. People might be working on it. It's going to have motors and all these types of things. But that's okay because it's on this passive spring. So this passive spring is going to act as a filter. And all that payload noise, or a good portion of that payload, is going to get filtered out. The surface here, which is going to be very quiet, which is where your sensor is. So you've got the sensor isolated from the payload, and it's not sensing that payload vibration, or very, very little sensing that payload vibration. Now you've got a whole lot of bandwidth available in the sensor, so that your feedback loop can start focusing on just floor noise. And what's also interesting about this configuration is that you have a force actuator that's a high resonant frequency force actuator. So it's a piezoelectric stack with no low frequency resonances. And you're not introducing resonances into that system. So what you have here is a very, very quiet inner mass and a very, very stiff system with no internal resonances. That gives you a lot of bandwidth. So whatever this floor is doing, and you're looking just down at this floor, you've got a ton of bandwidth to cancel. So that gives you excellent low frequency vibration cancellation. And that's the advantage of using a serial type system. But the disadvantage is, if you've got onboard noise, there's nothing you can do about it. You've got, which is why a lot of times we see stacked systems. We see onboard noise canceled by some parallel type system because it's known and can be done very well. But you see floor vibration handled by an active vibration cancellation platform. And here's the difference in the transfer functions between the two systems. You've got in red, you've got a parallel type system, and you've got blue being the serial type system. And this is only floor vibration transmission. So this is any noise coming up from the floor. And the way we model these curves, actually these are real measured curves, is by taking the transfer function from a known floor input to some payload that was a fairly not very noisy payload on top of the isolation system. And you saw what can be expected. In the parallel type system, you've got this amplification around 1 hertz, which is due to the system's own internal soft components. And when you start seeing isolation, it's around 1.5 hertz. But if you really want to start about significant isolation, you want to get down to 90% or 10 times reduction. You're not getting the 10 times reduction until you're hitting 5 or 6 hertz over here, which is a little bit high, especially for a lot of floors, which are resonating around 1, 2, 3 hertz. In the serial type system, you get a resonance, and this resonance is due to electronic controls. It's actually not due to a soft mechanical component. So there's a minor amplification at extremely low frequencies, which are actually not very common in floors anyway. So it's never been a problem. So but what you start to see is at 1 hertz, you're already isolating at about 50%. Once you've gotten to 2 hertz, you can achieve 10% reduction. So the trade-off for an extremely low frequency electronically induced resonance versus a mechanically induced resonance at 1 hertz is this difference from 10 times isolation at 2 hertz to 10 times isolation at 5 hertz. So this gap between the curves is the kind of performance that really makes a serial type performance, serial type system far, far better suited for floor vibration cancellation. So combining isolation systems. I've got two slides on combining isolation systems. This is the simple version where you're combining a passive system on top of an active system, for example. You can do them in a few different ways. You can do an active system on an active system, which we'll talk about later. You can do a passive system on an active system, or a passive system on a passive system. But to properly stack two systems, you need one of two criteria. We call it a separation of mass or a separation of stiffness or an impedance mismatch. And so separation of mass is a good example on the left-hand curve here. And what you see when you see separation of mass is something like those large concrete blocks supported by air isolators and rubber mounts that you then might put like a scanning electron microscope on. And what's happening there is a separation of mass. You've got a smaller mass, and it's your scanning electron microscope, and that microscope, or maybe it's an optical table, and it's got a set of air isolators in it at some small, low resonant frequency. Well, if you were to put those two isolators on another two isolators of similar resonant frequency, you're immediately going to be unstable. So what you want to do is put a big mass in between them. And that's what this concrete blocks becomes. It becomes a large mass in between two springs of similar resonant frequency. And that's how you get this, separation of mass. Another way to do it is with separation of stiffness, meaning you've got two isolation systems. They've got different spring constants. And if they're different enough, you don't need too much mass in between them. In fact, you don't need any mass. And that's an example of, say, for an optical table or a scanning electron microscope with a resonant frequency, say, around 2 Hertz. Well, if I place that on an active cancellation system, for example, that has a resonant frequency of the passive component, say 18 Hertz or 20 Hertz or whatever that is, that's a fairly big difference in the two stiffnesses of the stacked systems. And you get the separation of stiffness, this impedance mismatch, you're likely to reduce coupling, and it's easy to achieve stability. So that's what we do in this product, for example. It's a laser table base. This is a really good example of properly stacking systems, where you've got passive pneumatic isolators on one stage, and the lower stage is a hard mount active cancellation system using piezos and hard rubber mounts. You've got this impedance mismatch, and what you can do is provide a system that now has the best of both worlds. You've got the high frequency cancellation that's afforded by the air isolators, plus low frequency cancellation that's afforded to you by the low frequency performance of the active piezoelectric systems. And you can create some really, really interesting transfer curves that show really great isolation. So stacking systems can be done. And if you're looking for really good floor vibration cancellation, really the right way to do it is by using an active system at one stage and some sort of passive pneumatic system or active pneumatic system on the other stage. So let's switch gears and talk about instruments that need vibration control and how this vibration control affects these instruments. Here's a scanning electron microscope. And in its most simple example, you have a source of an electron beam shooting down a vacuum column, and it's being controlled by various toroidal magnets that induce a magnetic field that focus and move and shift and change the beam. And then it hits your sample, and you eliminate, the sample emits secondary electrons, you detect those electrons, you get an image. Well, most scanning electron microscopes nowadays are on some sort of air isolation system. And say you've got a vibration problem, maybe it's coming from the floor, maybe you push on the column. Well, there's resonances in all these components, and all this motion causes relative motion among components in the system. And you start to see this relative motion kind of misguiding your beam. And that beam can move left to right, front to back, up, forward and backward. And those mechanical effects on the relative motion from the source to the sample are what gives you crappy results like these on the left-hand side. And this is a really good example of floor vibration in an image. You can see where a train has gone by and caused that beam to wave back and forth, causing these waves. Well, we took the same electron microscope, which is installed at Portland State, and placed it on a vibration cancellation platform. Now you've got the air isolators still functioning in the scope, but they didn't provide enough isolation for this case. You place on an external serial type piezoelectric cancellation system, you now can cancel out that low frequency vibration, which is being resonated by the internal isolators. You cancel that out, and you can get a good image. Here's another really good example for wafer inspections. This is a pretty simple example of some sort of wafer inspection stage. What manufacturers of instruments that have moving stages in them try to do is, like in a step and settle type application, they try to get that stage to get to where it needs to be as fast as possible. You try to perform a measurement on whatever's on that stage as fast as possible. And then you're going to get that stage to the next place for the next measurement as fast as possible. And all this stop and start induces a lot of vibration. And you can't do your measurements if the thing is vibrating. So the goal for like a step and settle application is to try to cancel out the induced motion of the stage as fast as you possibly can. And we start talking about settling time in a step and settle application. We start looking at, well, what is the known input of your stage motion, for example, and how fast, how much power, how can I design an isolation system to predict how much energy it's going to induce into the frame and then cancel it out as much as possible. And this one we get charts like these where we're looking at, well, how is our active cancellation system performing? And this is a really good example of a model we used for a parallel type cancellation system. Now remember, the parallel types, they use feed forward and they use feedback as well. But the goal is to cancel, but their primary purpose and their best application is to cancel out known motion. And so what we have here is an example of a stage we accelerated in a test. So here's your acceleration profile of the stage in blue. You've got a displacement on the left hand, and you've got time on the x-axis. So here's your stage accelerating, hitting a place, hitting a location, stopping. It then moves and accelerates and stops, moves again, and then stops. So it had this motion, stop, and you get this profile of the payload relative position that you can measure. And when you have no active cancellation, then this is occurring on a 3 Hz pneumatic isolator. So these types of isolators here, and say they're just filled with air, you can measure that displacement. You get that motion of the stage, and you get the whole thing shifts this way, 40, almost 50 microns, and then the stage moves again, and the whole thing shifts 50 microns the other way. And once it does that, it's always going to want to go back and forth, and eventually it settles. So the goal is to take this motion and get it to go to 0 as fast as possible, or at least to some acceptable window. And so you use your parallel type active cancellation system with all these inputs to then start to interact, to start to act against the motion, and you can predict when you need to start engaging those motors to act against the known induced motion, known induced force. And that's where you start to see this red curve where the displacements are much lower and the settling, in this case, is much faster. So we've gotten to almost 0 at 0.4 seconds after the motion, as opposed to 0.8. So we've cut the settling time in half. So what does that mean? If you cut settling time in half, you can now take twice as many measurements in the same amount of time. Your wafer inspection tool is now sending through twice as many wafers. And that's a big deal for somebody like a semiconductor manufacturing company. So I'm going to switch into how we now build systems and talk about examples of how systems have built into OEM type instruments. And the key here is you want to think about vibration control early in the design process. We at TMC, we can do a lot of custom things, but we're bound by physics. And we've got to build an isolator that has the appropriate dimensions that can handle the mass and the loading and the motion that you're trying to cancel. We can do a lot of things custom, but the earlier you think about vibration design, the less frame redesign work you have to do, because these are all going into frames or underneath frames. But think about it early, start talking to us, because we've seen a lot. So, you know, what you want to try to do, there's really two things that you're trying to do when you're introducing, as an OEM, when you're introducing vibration control. The first I already kind of alluded to. You want to get that faster throughput to process more wafers, process more gene samples of biological samples for gene sequencing or anything like that. But another thing that OEMs can do when they're introducing vibration control, and I think this was learned many, many years ago when, you know, the OEMs started to put in air isolators and springs into the SEMs right off the bat, you can increase your addressable market. So when a user is bringing in a microscope and you're looking at the environment to see whether or not that environment has the right temperature and the right vibration and the right acoustics and the right magnetic fields for a microscope. Well, the vibration cancellation system is important because manufacturers are going to be going in there and looking at the environment and saying, okay, well, if you want to install our instrument, you need to provide this level of vibration control. And different manufacturers, depending on how sensitive their tool is to vibration, may or may not need to put in more vibration control. So you can effectively make things easier for a customer and make things easier for your sales team if you have a tool that already has the best vibration control built into it. And then that becomes less of a conversation during the sales process. So an end user looking at two instruments might say, okay, well, here's an instrument that has all its own built-in control. I don't have to provide an environment for this, so it's going to be easier for me to install. Versus here's an instrument that is going to require all these vibration cancellation mitigation options. None of it's built in. Why would I do that? I'll go with the manufacturer that has it. So we're trying to, you know, help OEM customers kind of understand this need for providing a tool that requires a less stringent environment is actually a competitive advantage. But I digress. Again, the key contributors to vibration control are mass, stiffness, damping, and the isolators that you use. And so mass and stiffness are actually very, very important, but because, you know, the more mass you put into a frame, the more stiffness you put into a frame, the less it's going to vibrate, and that's just intuitive. But they'll come to a limit, and they're also expensive, and also they take up space. So you've always got to try to worry about optimizing your frame. You can't make something too massive and too stiffness. At some point, your vibration isolation system needs to become sophisticated enough to start taking over for what mass and stiffness can't do. Here's one example. This is a simple integrative passive isolation system. These are used on interferometers made by one of our companies, sister companies, Zygo, down in Connecticut. And they're a fairly simple system. And this is the type of system that's very, very commonly built into scanning electron microscope frames, transmission electron microscope frames, NMR frames, these types of things. It's pretty commonly used in the industry. But you can see you've got a frame that was built here, and you can see these little discs that represent that top load disc of the air isolator. So it's a very simple design. Here's a frame. It's got 4 support points. It's got your isolators built in at those points, and you're off and running. So that's great. Pretty easy, pretty inexpensive, works at most frequencies, but pretty crappy performance at low frequencies because this is what we talked about earlier. These are just passive isolators, and they're going to give you these resonances at low frequencies. So if you're moving this into an environment where you don't have a lot of low frequency noise, it's 9 times out of 10 sufficient. But if you've got that low frequency noise, you're probably going to have to start thinking about a way to get this tool to work in that environment. And the best way to do that is active cancellation for low frequencies. Here's an example of a diamond turning lathe that is made by, again, one of our sister companies, Presitech, up in Keene, New Hampshire. This is a beast. It's a giant granite block supporting this moving arm, which is going to engrave some pattern on this drum for embossing optical films. And again, it's a passive isolation system, but you can see that what I like about this is that it's a scalable system. It's still a system that's going to be isolating at amplifying at low frequencies. But what we've included is some damping fluid, because this is a system that's going to have some motion of this large, massive stage moving back and forth. And so to help sort of resist that motion, it wasn't so aggressive that you need an active cancellation system to cancel out that stage, to cancel it out, because it's going to shake the whole system. But you're going to have some mass shifting over the course of the use of this this operation. And so it behooves you to have a little bit of damping fluid in these isolators to help them resist that a little bit more, which gives you more, which is going to give you something more along the lines of this blue curve here. So the first one, I'm using the same chart. So the first one was an undamped isolator, giving you this high resonant frequency in the red curve. We add some damping into these isolators. You get this lower resonant frequency, you shift it forward, you sacrifice a little bit of your high frequency performance, but then you get a little bit more resistance to that stage motion. And you can see how it's built into this design in a fairly crude way. Again, it's got 4 support points. It's got one here using 3 isolators, 2 isolators in front, 2 isolators back and back. So it's integrated into this entire frame that supports this entire granite system. Here's where things start getting interesting. There's ways to integrate your active cancellation systems. And so first 2 systems we've talked about were for floor vibration and getting that instrument into a place where it's being less affected by floor vibration, thereby affecting the addressable market for that system and allowing it to perform in more environments. This is the same thing. We're trying to cancel out floor vibration. In this case, we used a stasis serial type active piezoelectric actuator. So these are the serial type piezoelectric actuators built into the frame of this optical profilometer. And again, what you have here is a 2-stage isolation system. It's a set of air isolators that are damped, and it's a frame component, which is in this case a platform type frame component, and then your 3 isolators down here supporting that. So you've got this 2-stage isolation system. You've got active stage in the bottom for low frequency vibration. You've got a stiff frame, and then you've got 4 support points for the granite structure here that has the instrument, and those 4 support points are the are pneumatic isolators using giving you higher frequency isolation. Here's one for another type of tool, an anion-probe tomography tool, which is used, and what we have here is stasis built in even more into the frame. So you've got your active piezoelectric system kind of built into a pocket of the frame. And again, we're using the same stacking philosophy where you've got an active piezoelectric system sort of stacked in with this damped isolator. And again, you get the combination of the 2 transfer functions. So really good vibration isolation performance, and nicely integrated to the frame design here, so that when this tool is installed, you can't even see the isolation system, and it's a nice design. When we start talking about motion control, we start talking about different types of motion control. I kind of alluded to it when we talked about the diamond turning instrument, but here's an instrument, an example of an isolator used in life sciences, and it's actually kind of a small one that we make, but it's a damped die spring. And the purpose of a damped die spring is twofold in this case. We're providing transmissibility and floor vibration cancellation, but the operation done by this instrument isn't that sensitive to floor vibration. It is, and so you benefit. And so you got this green curve here, which is even more damping used. So what we have here is a very, very highly damped die spring isolator, and inside you got a little metal spring like this. So we've got a very, very highly damped die spring isolator. And we're not getting great isolation performance, but it's not a very vibration sensitive application. You don't really need that much floor vibration control for what this particular instrument's doing. High frequency, so we traded off a lot of that, but what you do need is fast settling time. So we put a lot of very, very viscous damping fluid in there, and we got it to a place where without using linear motors or making a very sophisticated electronic feedback and feed forward type of cancellation system, just by using a viscous damping fluid and by varying the damping of that, you can achieve settling times just by virtue of the damping alone. And in this case, a settling time of roughly 0.5 seconds or so was good enough for this application. So it's not a highly sensitive vibration to vibration, but it is sensitive to settling. And so you can achieve that by putting in damping fluid, and sacrificing isolation. And here's a good example. My last example, almost my last example. I'm sorry, starting to run out of time here. This is a parallel type system used in stage cancellation. So I just wanted to share a photo of the example that we showed before with the wafer inspection type tool. And this is a kind of a very common configuration where you have an air isolator here, but that air isolator is buried beneath these two linear motor type isolators where you have ferromagnetic plates and electromagnet inside, and that's used for this very, very aggressive force application to cancel out a known stage motion. I explained this graph before, but what you're trying to achieve here is a stage moves from left to right, for example, and you know that that motion's coming and you know that impact's going to happen. So you can start to get this linear motor to get charged up, and it starts to exert a force before that even starts to happen. And these very complex feedback and feed forward type control systems can give you very, very, very good settling time. And there's a third way to do it. You can do a similar type of cancellation, but your base isolator is not necessarily a pneumatic isolator, as it was in the previous slide. Your base isolator is a serial type cancellation system. So this is pretty unique, but if for some reason air is not going to be a good base isolator for you, where you need even more stiffness than air can provide, or you want to combine, or you don't want to deal with that low frequency resonance that's induced by the air in your isolation system, and you want much better floor vibration control in addition to the motion control, you can kind of come up with a serial type system with a linear motor in parallel. And that's what this interesting guy is. We have a serial type system, and here's your hard mount passive stage. Here's your sensor and your piezoelectric feedback controlled actuator. But in parallel, we put a linear motor here. And so we're controlling, so now this is the only way you can really use a piezo serial type system to control payload noise. You've got a feed forward signal through through acting on the payload, but still the control loop and the sensing of this piezoelectric system is actually still not influenced by the payload. So you can achieve very aggressive settling times. In this case, we've got a typical settling time on a serial type system on the left-hand side here. So you put it on a regular serial type system. Remember what I said, serial type systems are unable to act on the payload. You've got a fairly slow settling time of 800 milliseconds. Well, you put that linear motor in parallel, you've now got you can achieve a 200 milliseconds settling time, which is extremely fast, especially since you've got a hard mount isolator, not a soft isolator in there to contend with. You can really get a lot out of that linear motor. My last slide here is just an example of something we've seen folks trying to do, and I just want to clarify it. You can integrate systems, or you can stack systems. If your and this is particularly important if your goal is floor vibration control. And there's two ways of doing it. If you've got vibration coming up from the floor, and you've got, say, a scanning electron microscope on its own passive isolators, you can, and we've seen some people do this, literally bolt some linear motors onto the sides between the payload and the frame, and come up with some sort of feedback system and make a parallel type system. And that's all well and good. You can do that, but you're going to achieve the performance that we talked about before with parallel type systems. You're going to have a real hard time getting isolation at those low frequencies because you still got the resonance of this load-bearing air isolator in the game. You can get some damping and make it less sensitive to low frequencies, but it's definitely not going to be isolated. So if you really got low frequency floor vibration, the right way to do it and the way to really maximize the performance of your systems is to stack them. So you put an active piezo system here, which is this section down here, and you can still benefit from the high frequency isolation from the internal air isolators. And so stacking allows you to then generate a combined system that has very, very good low frequency performance, in addition to doesn't cost you performance at high frequencies. So in conclusion, I've got 3 bullets. Vibration that affects ultra precision equipment comes from a variety of sources. Each source requires its own mitigation techniques. And the key is to plan for vibration control. You want to engage your vibration solutions expert early in the stage to identify, design, and manufacture it. The earlier we talk to you guys, the better we can integrate that into your frame, and the better it's going to work out for a lot of reasons. So that's those were my that was the webinar. I wanted to thank you all for attending, and we've got 1 minute left. Sorry for the short, the going long, but I'd love to field any questions.
Thanks, Mike. Yeah, we have a question here. It's for those OEM customers you work with now, how do you keep up with their demand? Do they give you a forecast of how many platforms they are going to need in a year?
Yeah, that's a good question. The semiconductor market, as we've all heard about, the chip shortage has really led to a lot of manufacturers of semiconductor tools, especially also SEM and TEM and e-beam lithography instruments. All these guys, they're all seeing huge ramps driven by semiconductor chip shortages. And we work with all the major OEMs, and we're supplying vibration cancellation systems for tool vibration and for floor vibration. And we too have had to ramp the factory to meet those needs. So forecasting is very important. You know, sometimes there's a lot of visibility in semiconductors, sometimes there isn't. But the best we can get for forecasting helps us line up our labor, helps us line up our supply chain, helps us meet the needs. But I think everybody, if you're an OEM and you're on this call, you probably felt the semiconductor ramp. So we're here, we're here for it too. So we want to work with you guys to make sure you get your products on time.
Okay, thanks. I have one more. If anybody has any more questions, please, type them in. But the other one I have is, I think you covered this, but what do you see as some of the advantages of outsourcing the design of our machine's vibration control platform to TMC? Like, why should we do this?
Yeah, that's a good question. Well, TMC, we're a team of vibration experts. We're engineers. We've worked with these a lot. And I think the reason why people come to us and why someone should come to us when they're designing an instrument and they think it might need vibration control is vibration control systems can be complex. They can be very simple. But when you're designing an instrument, you want to focus your efforts on getting that instrument to do what it needs to do the best way. You want to think about your lithography technology or your electron microscopy technology. You want to think about your technology. You don't want to be trying to develop from the ground up some sort of vibration cancellation system that is going to be part of your tool. I feel like that's a waste of your effort. Why don't you come to TMC? We've got a lot of expertise and a lot of manufacturing capabilities to develop really the best solutions. We've been iterating designs on these types of things now for 60 years. Let's try to figure out a way to work with us and build into your system so you don't have to worry about that. And that's why I advise people come to us and have us do it.
Okay, great. I got another one here. Can you give guidelines on how to handle damping of payload-induced internal flexible modes?
We probably could. And it just depends on what the payload, what is it, what is that motion inducing that flexible mode, and when the way the question is phrased is a little bit vague, but I'm thinking, it sounds like you got a mass and it's moving from one place to another and it's causing the frame to flex when it moves. And flame flexure and frame torsional modes due to, mass and from moving from one place to another. If it's the mass causing the flexure and it's a static flexure once it's been done, then I would say that the recommendation would be just make that frame stiffer and make it more massive. If this is something that is moving and causing an impact, and you want to try to stop that, we want to try to minimize that impact from that motion, then you might be thinking about some sort of active cancellation. So it's a vague question, but I would be interested in learning a little bit more and having a deeper discussion. So yeah, shoot me an email and we'll start talking about it. But I like this question because it's kind of an example of what we like to do here at TMC. We like challenges, we like dealing with stuff that's new, and if you want to have a chat about a vibration problem, you're not going to get sold immediately. You're going to talk to somebody that wants to figure out what you're trying to do, and I think we should talk a little bit more. So let's let me get your contact info and we'll talk on a little more.
All right, thanks, Mike. And I think that's it. As Mike said, yeah, if anybody else has any questions, feel free to reach out. And thank you so much for attending.
Of course, yeah. Thanks, everybody, and have a great rest of your afternoon. Thanks for attending.